So hi everybody, my name is Lionel, and today as an industry insight we'll do something a bit different since I will be speaking very shortly about our company and our. And then I will share the stage with Siamak, one of our customers who will present. So, agenda, I will first spend a short time about Groupe T2i, who we are, what we are doing. And then I will share the stage with Siamak from EPFL-LMH, who will present a new finite volume particle method that they have developed for CFD computations. So for Groupe T2i, some quick facts. So we are an IT software editor and IT services company. It's a holding of 7 companies. Some of them have been on the market since more than 30 years. We are around 200 employees, and we have more than 250,000. As regards the market we are addressing, we are covering about all the important markets in Switzerland, like public and academia. We address companies from all sizes, from small, very small.
This one, if we check, yeah. It's going on and off.
So, sorry for that. And so we are covering also the 3 French-speaking territories, which are Switzerland, France, and Canada. As regards the solutions more on the software side, we are working around electronic document management, content management services, workflows management, all the human resources processes, either as software or as outsourcing, and everything around IT modernizations, where we fit the HPC AI things. And so the company is structured around 5 business units. Most of them are addressing verticals or cross-market, and there is one infrastructure and cloud unit, which I'm part of, and which is the one which is handling everything which is around infrastructure, and thus HPC. We are doing everything related to value-added reselling, so we're reselling, hosting, managed services, software as a service for our own solutions, and also, let's say, one-time services, which are mostly used also for HPC. Now, about what we are doing, in particular in the HPC world. So we are IBM and Lenovo business partner, NVIDIA preferred partner, and Open Power Foundation member. We have a very strong relationship with the vendors and a very deep technical knowledge of their products, which is something that not all partners have. As we got our HPC reach, we were focused until today on the academic and research, but we are going more and more trying to address the commercial world also. What we love is heterogeneous computing, everything which is acceleration through GPU, like the project that Siamak will present, also FPGAs, and we like everything which is high speed, high throughput, low latency. We're also quite interested in the new cognitive computing thing, so AI, machine learning. We're also as an IBM partner, we're also covering IBM Watson, and we have also some predictive analytics and analysis solutions. If we look at what we can provide as a partner to our customers, so as a pre-sale services, we are covering the 5 main phase of a project, so which starts with exploration. So we are able to come to customers and do presentations, and we can organize workshops with the vendors and key people from the vendors. And we are also doing brainstorming about what will be the best solution for a particular project. After that, we have also the testing phase, where we have some own machines where customer can do tests and evaluations. And we're also well connected to our vendors like IBM, where we have access to, for example, to the NVIDIA IBM Acceleration Lab. And we are also able to put customers in contact between them for those who have already bought machines and are happy to help. We are also covering the design phase. So as you know, storage and networking is an important thing in cluster design. And what is somewhat overlooked, but is quite very important in particular to get the best performance and the lowest cost, is all the rack layout. So we are very deeply engaged with deep technical knowledge on how do the best rack layout and to minimize. And this leads to the pricing phase, because you finally have to buy your cluster. And so here we are doing a continuous optimization process, and we get support from the vendors for a particular project. And since we speak about optimizations, it's always an ongoing process, and it takes time. As you know. Once the cluster has arrived on your premise, we are also able to help there. So we do everything related to physical installation. So we are expert in cabling, as I already said. We do also the software deployment part, so basic operating system and libraries and tool chains installation. We use automated tools like XCAT, which we are good at. We do also afterwards all the cluster configuration and the storage configuration. We are one of the best partner for GPFS and founder which is called Spectrum Scale. And we are also covering, which sometimes is overlooked, which is the monitoring. So either on the infrastructure networking part, but also the performance. Okay. And so now I will give the stage to Siamak. So with that project, we used around what I call, so we identified in the exploration phase that they were creating a new algorithm, a new kind of algorithm that were using GPUs. And so since we were aware of the plans of NVIDIA and IBM for the end of last year, we told them, hey guys, wait, you have a new kind of machines at the end of this year. So they did tests on our machine that we have on site. They saw that it was easy to port to power and that the GPU was working. So we started a project, they finally bought a machine, and they developed GPU-SPHEROS.
Thank you, Lionel. So good morning, everybody. I'm a PhD student at EPFL Laboratory for Hydraulic Machines. So we are developing an application for fluid flow simulation on hydraulic machines like external flow in Pelton turbines, this kind of stuffs. So I will introduce our work to you here. Then first I will talk about the free surface, large and large boundary deformation problems. Then I will introduce you our method and the advantage of the method. We actually use it. And then the CPU version of the code, which the name is SPHEROS, is developed since 2010 in our lab, and we switched to GPU version to speed up the application, which is really computationally massive because of the algorithm. And then I will report the speed up of using the installed version by T2i with NVLink and 2 Pascal-based architecture GPUs. So, as you see here, the laboratory is a laboratory for hydraulic machines. So, the Pelton turbine can be a good example of the hydraulic machines for high amount of head. So in this kind of problem, we have free surface and we have large deformation of boundaries. So generally, the particle methods like SPH works for this kind of problems very good. But there are some disadvantages with the SPH method. So we switched to finite volume particle method, which is both conservative and consistent. Here you see the governing equation. Of course, we solve the mass and momentum conservation equation. And if you can change these two equations for the mass and momentum conservation to this form, and then you discretize and solve the problem numerically. But the advantage of our method, which is finite volume particle method, is conservative and consistent, which SPH is not actually consistent. So it's a very good point of this method. And this is really like all particle-based method is really robust in handling free surface and moving boundaries, which you have the problem to handle in finite volume method with you need remeshing, or you need to control dynamic mesh, which is not very easy. And for capturing free surface, you need a very small mesh, which also is not easy task to do with the accurate solution. But the disadvantage is high computational cost, so that's why we actually decided to go with GPU many-core architectures to further speed up the application. So here you see a movie, an animation of the Peloton simulation, which is with SPHEROS. It's the CPU version, which is versatile and is able to simulate the interaction between fluid, solid, and silt. You see here there are some sediments impact the particles, the solid particles here, and the simulation is actually transient, so this is really time consuming. And I will talk about the algorithm. This algorithm is not easy and very time consuming, so there is a very great need for a speed up for this method. So for the GPU-SPHEROS, the overall algorithm has three main parts. The first part is actually OAK3-based neighbor search, which I developed at the first. And I started from the scratch because the CPU version data structure was very difficult to import to the GPU directly, and the algorithms was not well suited for the GPU. So first you'll find the neighbors of each particles. Then you compute the interaction vectors of each particles, which is here, and this most time consuming part is 67% in terms of time. And then you compute actually the different discretized variables here, like velocity, pressure, everything. And here you see the interaction vectors, delta ij. This is really needed for the next part. And this is the main difference between our method, the finite volume method, and actually SPH. And the formulation here causes the method will be both conservative and consistent here. So for finding the neighbor particles, I implemented an OAK3 on the GPU. So it's based on a space filling curves. We generate the Morton code of each particle and find the neighbor branch based on their Morton codes of each branch, and then we check the distance between each particle. So you see if you connect the particles, it will be like Z curve. And there are many implementation of OAK3s on the GPU. But anyway, we implemented ourselves and we got a good speed up for the neighbor search actually. And the good point of this part is we sort the particles for the next part to have a coldest memory access. Not very coldest, but it's really improved the memory access which is necessary for the GPUs. For the next part is computing the interaction vectors is the most complicated part of the algorithm and most time consuming part of the algorithm. If you have some spherical support for the particles you see and the neighbor particles you see, you need to find this vector here, which is something similar to area vector in finite volume method. So for one particle, you have 40, 50 neighbors, and you need to find all of these vectors between each particle and its neighbors. And we have different kernels, like 20 kernels from beginning to the end of the algorithm to find these vectors for each particle. This is not a cubic. We implemented the spherical support, which is algorithm is much more complicated with the cubic support for the particle. But there are some advantages you see here in terms of physics and accuracy. Actually, it has higher accuracy, 1 order. But the algorithm is more complex and 1.5 times higher computational time comparing to cubic support. But it's already implemented on the GPU and gets a good speedup. For the solver, here I actually put just one animation to show you how I validated the software, how I validated the solver. It's a cavity problem, which is benchmark in the CFDs. And here the wall is moving with the velocity to the right side. And this is a contour of velocity magnitude in this Reynolds number. So the particles, I just put the particle fixed here, as our method is arbitrary Lagrangian Eulerian method. So I can just put the x dot, because for the cavity there is a difficulty with the moving particles because you will have some hole here. But anyway, I want to just check the solver and computing fluxes works good or not. So the solver is already validated actually, so the algorithm is totally works now. And for the optimization of some kernels, and most of the times we have compute-bound and memory-bound kernels, so the optimization strategies will be different for these two kinds of kernels here. There's two examples: the weighted least square kernel, which is compute-bound, and volume integral gradient kernel, which is memory-bound. After the optimization, I checked the speedup with the CPU version, CPU implementation. Here, I use Kepler architecture, Tesla K4D compared with Intel's on this model, actually. And you see the speedup. For the compute bound, it was much more easier to optimize, but for the memory bound, it's a bit more challenging, as you need to control your data access, your memory access. It is very, very important for the GPU, as all you know. So in this slide, you see the procedure of the implementation of the GPU-SPHEROS. We were two. One, the CPU version developer, and one PhD student, me. We started with the octave neighbor search. Then we added the octave neighbor search, and after doing the octave neighbor search on the GPU, we transferred data to the CPU, which is itself a bottleneck. So we really wanted to avoid it, but at that moment it was not, as the code was not totally implemented, so it was not possible. But anyway, for the next part, I implemented computing forces and fluxes, optimized some kernels, and then we went to the main part, which is interaction vectors, and was after we finished the code, it was 85% of the whole code, which was actually the bottleneck, which was the priority for the optimization. So we applied some optimization. I don't go to the details here, but we applied some optimization to the interaction vector parts, and this part actually, and the percentage you see here changed, and here you see the final global speedup comparing the system. We used the 2 Pascal based architecture GPUs and Power 8 CPUs, which NVLink between both GPUs and CPUs installed by T2i. Thank you to Lionel here. And I compared with one CPU node with 2 Intel Xeon CPUs inside with 20 real cores, and with hyper-threading it's 40 cores. So the speedup is 7.7, which is really good. It was a good achievement for us. But still, there is a great potential in this part. Actually, we can optimize this part more. And this is the speedup. The code is not very stable. Actually, we work on optimization every day. So the speedup here is a bit, is 9.3, 9.4. I compared with the same CPU node as in the previous slide I showed you, but the speedup increases and increases. So finally we reach about 10 times faster code on the single GPU comparing to one node CPU. It means that it will be faster more than 10 CPU nodes because you have communication between CPU nodes. So, and I compared here for your information also this speedup with the Kepler architecture, and Tesla K40 is 4 times slower than this Pascal here. And here you see the throughput is 362K particles is computed in 1 second with the one single GPU Tesla P100 and using NVLinks also. But anyway, we really manage in the algorithm to be able to keep the data on the GPU memory to avoid communication between CPU and GPU memory, which is actually a bottleneck. So this is the speedup at the moment we have. So we are going to multi-GPU version to develop the multi-GPU and run a real scale simulation with billions of particles. This is the goal. And for the summary, I would say the finite volume particle method is very compute intensive. So that's the main reason we decided to switch to the GPU many-core architecture. And the GPU versus the GPU version is GPU accelerated version of the CPU version of the code as the GPU accelerated version of the SPHEROS. And I showed the results with GPU-SPHEROS and SPHEROS. And the speedup we achieved comparing one GPU and one CPU node. And we use 2 Tesla P100 GPU at NVLink between GPUs and CPUs. The NVLink is, the bandwidth is 80 gigabytes per second, so normally it's 4 times faster than PCI Express. And it's really useful when you want to save outputs. And the code is not as stable as I mentioned, and there is a great potential for the optimization and computing interaction vector part. So after the multi-GPU system, we're going to more optimize the kernels in the spherical support interaction vectors computations, which is 60–70% of the code, and for sure it's a bottleneck. So thank you very much, and if you have any question, I can answer. Thank you.